So good morning, everybody. It's a pleasure for me to introduce Thomas Grimm from Utrecht University. And Thomas will start today's morning session with telling us something about tame geometries in QFTs and string theory.
Well, thanks a lot. First of all, I would like to thank the organizers for putting together this conference and to inviting me to speak here. And what I'm going to talk about is some exciting subject which I've been working on for the last 2-3 years. And admittedly, it is not directly related to the main topic of this conference. However, I will touch upon integrability towards the end of my talk. And what I hope to do with this talk is I hope to give you an understanding of at least what it means to use tame geometry in physics, in quantum field theory, and in string theory. And I hope that you will share a little bit of the excitement which comes from this discovery. It will be based on a number of papers. Well, in fact, it was inspired in this first work, which is done together with three pure mathematicians, Ben Bakker, Christian Schnell, and Jakob Zimmermann. And it kind of working on this, it led me to suspect that kind of tameness is actually something which is omnipresent in physics. And this led to this conjecture here. And more recently, in an upcoming work, we actually show quite remarkably, I think, that indeed tame geometry is very useful in quantum field theory, right? In theories without supersymmetry, in very general settings. And finally, I will comment on some work done in collaboration with my PhD student, Jeroen Monet, who is also here in the audience. And this is kind of connecting this story into integrability via Hodge theory. Let me start with a very general introduction. Well, when we start to study mathematics or physics, we realize quickly, at least from the experience from school, that mathematics is wild. Yeah. Especially when you learn analysis, we realize that topologies and maps can be really involved. They are used as counterexamples for all kinds of simple thoughts. And we learn about complicated sets, for example, Cantor sets, which are kind of infinitely refining sets. We learn about complicated functions, so mathematicians have no problems with these sort of functions, which are jumping at infinitely many places and so on. Or this function, which is kind of roughly depicted here, not really, because it kind of gets infinitely dense, infinitely many zeros. So this is what we learn in mathematics. And a common feature of this is that there's no proper graphical representations. I mean, I can do something like this, but at the end of the day, I'm missing the main point of this function, namely these infinitely many accumulating zeros. Now, if you dive deeper into mathematics, namely you learn about logic, things get even more wild, right? Maybe you have learned about or heard about Gödel's first incompleteness theorem, and you learn about that statements can be undecidable, like fundamentally undecidable. You can neither prove them or disprove them within the axiom set. Yeah. That sounds very, very wild, and it was also shocking to mathematicians at the time, of course, and there's much work subsequently focused on this. But then, once you learn this in your original lectures on, say, analysis, you start to study physics, and then this kind of fades out, this information, right? And in fact, one has the feeling that physics must be more tame. right? It shouldn't be that crazy. This thing shouldn't be very physical, right? Yeah. Okay, it's a good feeling to have, and I think we all agree it's probably true. But what is a proper tameness principle? I just realized I'm standing in the wrong side of the room. What is the proper tameness principle? Okay. And in this talk, I want to tell you what could be such a proper tameness principle. Now, how did I come to think about this question? Obviously, well, I didn't sit down and look into analysis book and think, oh, there must be something interesting there. No, how did I come to this? Well, I actually thought about the number of effective theories or vacua which arise in string compactifications. Namely, there is a long-standing question in string theory and string compactification. Namely, is the number of distinct effective theories from string theory below a fixed cutoff scale finite? Yeah. It was proposed long ago in the beginning of the 2000s that this should be the case with some appropriate understanding of finite cutoff. And in fact, there has been much recent progress been made in this direction in the context of the so-called swampland program, which tries to kind of restrict all the theories which come from quantum gravity. Okay, there have been a lot of works in this direction, and that's actually where our mathematics paper is centered. So it actually answered one of these finiteness questions in a very specific, precise way. Namely, what we studied is we studied certain flux compactifications. I will say a few more words about this later on, with self-dual fluxes. And we actually prove a rather non-trivial theorem, namely that there are only finitely many of these. And in fact, that kind of translated into more physical terms, that these scalar potentials which arise there have only finitely many minima. So this crazy wild function which I gave you on the first slide actually shouldn't appear because it has infinitely many minima. So a finiteness criterion could be a nice tameness criterion, yeah, because it would rule out one of these functions which I gave you before. But finiteness seems at first just a yes or no statement. Yeah, something is finite or not. So it would be much nicer to have something structural, something which you can work with in your theory in general. Yeah? And therefore, one can be inspired by this proof of this finiteness theorem. And in fact, this proof of this finiteness theorem uses a very powerful mathematical machinery which is currently investigated to a very large extent, namely the so-called, or you might want to call it tame geometry, or O-minimal geometry. So what do we observe? Well, with this kind of approach, you then realize suddenly that, in fact, that if you go through all the effective theories which we know from string compactification, that in fact, if you fix the energy scale, then using this tame geometry, you find that they have tame coupling functions, they have tame field spaces and parameter spaces. Yeah. So you just go through the examples and you just see this. Yeah, it's sometimes really hard, and I will present some of this evidence. Then, if you look at quantum field theories, and you compute arbitrary loop amplitudes at fixed loop order, then you find that these expressions are actually tame functions. They are not as wild as you can imagine from your analysis course, but they are rather tame. And thirdly, you also find some tameness results when you look into integrable models. So in fact, in our recent work, we connected some specific integrable model with Hodge theory, and as we will see, tameness is kind of all over the place in Hodge theory. So actually, tameness also appears in integrable models in an intriguing way. So now obviously I step by step have to introduce what I mean by all of these words. So the first thing which I should mention is, what do I mean by we are talking about tame coupling functions? What do I mean by this? Well, let us look at an effective theory, some Lagrangian of this type. Then it can have some scalar fields phi, and then they might couple through a metric. Right? They might live on a non-trivial field space and might couple through a metric like this. And this metric might depend on the fields themselves, so it could be a curved space, and it might depend on some parameters, which I call lambda. Furthermore, you can have a gauge coupling function, which depend on phi and some parameters, or you can have a scalar potential, which depends on the fields phi and some parameters. So we have a parameter space called P, and a scalar field space called M, which can also depend on the parameters. Okay. So what is the kind of the setting? You have a parameter space and field spaces, and your effective theory changes over it depending on what kind of point I fix in these spaces. Okay. And now you can imagine all kinds of things. What are parameters? The number of fields could be parameters, or the VEFs of some heavy fields, or fluxes in the compactification, topological data of some manifold which is appearing in the compactification. So they are possibly discrete and infinitely many, yeah, in principle. So now what is this tameness statement? The tameness statement is that actually these field spaces and these parameter spaces and these coupling functions are not general functions and not general spaces, not general manifolds or something like this. But they are rather tame sets or tame functions. Okay? I will explain what tame means in a moment. But before doing that, let me already mention one key feature which we should keep in mind. I told you that we're talking about effective theories, and there is a cutoff dependence. Yeah, so an effective theory depends on which cutoff I'm choosing. And now you could imagine that you just lower the cutoff. Yeah, you say, oh, the highest possible energy scales is reduced now, and then you have to integrate out heavy fields. And that means that you're kind of flowing to a new effective theory. Yeah, you have to introduce a new effective theory. And the basic question is, well, this effective theory could have fewer fields, but it could have much more complicated coupling functions because you have to integrate all of these out. Okay? So one key feature of this tameness story should be that it's preserved under lowering the cutoff. So in fact, it could be that you start with a theory which has this field space, which I depicted here in gray. But if I lower the energy scales, I actually I locate myself into the vacua of the theory, and then I just get a discrete set, for example. Or I might get some flat directions. Yeah? And in fact, this tameness observation says that, well, all of these effective theories which appear starting from a UV theory should remain tame. So this tame geometry should have some very powerful features which preserve tameness under lowering energy scales. Okay, so now, yes?
But you can actually, suppose you have perturbative geometry theory, you can compute loop corrections and see what kind of functions you get. Yeah, so the question is whether you can actually check this directly, starting from some Lagrangian with some functions, computing loop corrections, and seeing what kind of loop Feynman diagrams give you, what kind of functions, what kind of integrals, and then this question is decidable.
Yes, exactly. Yeah. That's exactly what we are doing. So we are starting with the classical story, and then but it's very non-trivial, right? Because you could imagine that that hell breaks loose in quantum field theory, right? Because we have also very little mathematical deep understanding of quantum field theory. Okay, anyway, yeah, you're absolutely right. So now now after all this tameness talk, now I should finally tell you what tameness is. So the name at least and the idea, the basic idea came from the work of Grothendieck, who actually wrote a grant proposal, which is a sketch of which is called Sketch of a Program. Yeah, it's a grant proposal to go to the IHES, and his idea was that much of the mathematics or the topology which is used is actually developed for people who do analysis, right? But we want to develop a topology which is usable or useful for people who do geometry. Yeah? And that means you can draw things in a rough term. So especially we want to remove pathologies which occur in ordinary topology. In parallel and completely independently, there is was a development in logic, yeah, which discussed the theory of so-called O-minimal structures. This was developed in a part of logic which is called model theory. Okay, and it maybe you can trace its origin to the following question: you want to build a theory which has only decidable statements, okay? Only decidable things. And then this means in order to avoid this Gödel incompleteness, you cannot do this over the integers. That's where this sort of undecidable comes from fundamentally. But you have to work over the real numbers. And in fact, already in the 40s, Tarski looked at theories built from polynomial equalities and inequalities, and then showed that these are only leading to decidable statements if you translate them into logical statements. Okay, and this is a very, at least at first, a very simple setting. It's called semi-algebraic sets, and the important thing is that you need an ordering, right, in order to define inequalities. So this, as we will see, reappears because the O minimal structure means ordered minimal structure. So the ordering is central. Okay? And later on, it was asked, what are the interesting extensions of these simple structures? And the resulting picture was the introduction of O minimal structures. And they were shown when you translate their meaning in logic into geometry, that they define, in fact, something very similar to what Grothendieck envisioned, namely this tame topology. Yeah. In fact, you will see in a moment that they have strong finiteness properties. Yeah. They give a generalization of real algebraic geometry. So it will not just be polynomials, very important, because physics is not just polynomials, as you will see. So it's really a generalization of real algebraic geometry. And if you want to learn a bit about this, I very highly recommend the introduction book by Van den Dries. And of course, since you are here in Berlin, or we are here in Berlin, some of you are local, one of the world experts actually here, Bruno Klingler, in the math department, working on O-minimal structures and Hodge theorem. Yeah? So there are also, nowadays, you can find everything online, so there are very good YouTube lectures by these authors, by these mathematicians. Okay, so what is the basic idea? The basic idea is to specify a collection of sets, which we call tame sets, and allowed functions, which are called tame functions, and these sets are subsets of Rn, and the functions are f going from Rn to Rm. Yeah? And once you have this, you can use this as a starting point to build a tame geometry, and then you have transition functions on manifolds, which you can make tame, and so on. And you can build tame manifolds, tame bundles, and so on. So you can just develop a whole tame geometry. In a first step is we have to say, what are now these tame sets? So they first have to define a structure. So what is a structure? It's a structure it's a construct where you say, what are the properties of the sets within this collection of sets. And in particular, you want them to be closed under finite. I made this blue. Finiteness is very important. They should be closed under finite unions, intersection, complements, and products. So take two tame sets, intersect them, right? On their overlap, it should be again a tame set. Yeah. One crucial property is it should be closed under projections. So what happens if you take your any set, take a higher dimensional set, and then you project it down to a lower dimensional set, kind of a line, say, then the linear projection towards this set should be again in this structure, should be again tame. Okay? And in logic, this would be the existential symbol. And in order to make this set sufficiently rich or kind of extend what this tasky construction of kind of just using polynomials, we require, to make it non-trivial, that all solutions to polynomials equations are included from the start. Okay? So it's already quite a rich structure. And now comes the question, so what is now tameness? Tameness is actually not part of this. The tameness is actually just this simple assumption, namely that if you project, or if you look at the sets of R, of the real line, R1, then the only tame sets in this R are finite unions of intervals and points. These intervals can be infinitely long, but that's it. Yeah? Finite unions of points or intervals. So now, how does this tameness kind of go to higher dimension? It goes to higher dimension because we demand that everything is closed under these projections. So if you project down to the real line, everything has to go to one of these sets here. Yeah? Every higher dimensional set has to project down to this one of these sets. Okay. Now, how are we in time? Okay. So now, what are tame functions? Tame functions are those whose graph is tame. So just take a function like a polynomial function, and then if this graph of this function defines a tame set, then this is a tame function. Okay. So now I give you an example and a non-example. One of the examples is a polynomial function. So the graph of the function is just this. I take a simple polynomial, and this is by definition a tame set. Yeah? And in fact, you also see that if you project it down to the real line, to any real line, you get only finitely many points and intervals. Yeah? So it's totally consistent within the structure. A non-example is the sine function for x on the real line. In fact, you see immediately that if you project down to the real line, it has infinitely many zeros.
And by projection, you mean restriction? Not like a projection?
No, I mean restriction, so it's just a linear projection. Yeah. So it has infinitely many zeros, it is infinitely minima and maxima and so on. Yeah? This is not a tame set. It's never a tame set. Whatever you do, whatever structure you pick, tame structure you pick is never a tame function. Yes, that's
You only need the period to define the formula.
yes, yeah.
It's strange that sinus is not a nice function.
Exactly. So it's so you can have exactly 2 points of view on this. So the first thing is you're ruling out the sine function which appears everywhere in physics. That's wild. Yeah, that's not good. Let's put it like this. Yeah. On the other hand, you have, as we will see in a moment, there is a way of repairing this. Namely, if you say that actually the periodicity is actually something which is non-physical, then you can resolve this, and you can show that if you restrict the period, it becomes a tame function if you pick the right tame structure. please be patient for a few more minutes and you will see. Now, there is a theorem. It's a fundamental theorem. It's not too complicated to prove in tame geometry. So what does a tame function look like in one variable? A function from R to R. Yeah? You can show that any tame function is of the following form. You can split the domain into finite number of intervals. And within these finite number of intervals, the function is monotonic and continuous. It can jump, but it can jump only at finitely many places. So it can have finitely many discontinuities. In fact, you can show all kinds of corollaries to this. So one thing is that it has only finitely many minima and maxima if it's differentiable. Yeah. More interesting is you realize, since you can always cut the domain into finitely many intervals, there will be always a last interval, namely the interval which goes to infinity. Yeah? And along this infinitely long interval, not much can happen. It has to be monotonic along this. So there has to be a tail to infinity which is rather well-behaved, yeah? Which has a very tame behavior. Okay, that's one result. And now, unfortunately, this is one of the few places where you see the power of tameness. We just will observe tameness mostly in this talk, but it's very powerful. So once you have tameness and you combine it with something else, oh, I should have written tame here. If a function is tame plus holomorphic, then it's actually a polynomial. So it's not just, tameness is not just some kind of a nice observation which is not useful. In fact, it's very powerful if you combine it with other properties like analyticity. And here you see this very, very remarkably. So note, there is not a unique choice of an O-minimal structure. Actually, much of the early work on this in the end of the 90s and many of the deep theorems proved in this subject are about constructing such tame structures. And this is very non-trivial. It's done by logicians, and don't ask me how this proofs works. But the basic idea is to construct these sets by stating which functions are allowed to generate the sets. And that's very non-trivial to pick the function. So what are the important examples? Well, the first one is the simplest one, namely the one which is just generated by real polynomials. Okay? So you take a polynomial equation and put them equal to 0 in n variables, and then because of this projection property, you also get all the inequalities, and if you collect all these sets, this is a tame structure. This is the smallest tame structure, yeah, or minimal structure. Now, there is one, and that was kind of a big breakthrough in the 90s by Wilkie, that actually it's not just about polynomials. Actually, you can add transcendental functions like the exponential function to the story, and it still preserves tameness. And this is remarkable and very useful for us. So if I would have told you that that the exponential function is not tame, and we see it all over the place in physics, you would have discarded this immediately. Okay. So we are fine with the sign, with infinite sign, but with the exponential we need it. Just think about instanton corrections. So this is a tame structure, but there is an even bigger tame structure. So note that the game is now to make the structure as big as possible, to include as many as possible sets while still preserving these finiteness properties. Yeah? And that's the non-trivial task. And in fact, what you can also add is restricted real analytic functions. So take a function which is analytic, and restrict it to a smaller set, to say a smaller interval, and use it to generate your sets. And this is an O-minimal structure, a tame structure called R-unexp, just a name. Yeah, un means analytic or restricted analytic, x means that the exponential function is included. So how do the sets look like? Well, they are generated by finitely many equalities and inequalities, which contains polynomials. So these are polynomials. And you can use the exponential function, and you can use any restricted analytic function. So why is this structure so important? Yeah, so in fact, this will be the most important structure. It will be the most important structure because it is this structure which makes the complex exponential into a tame function if you restrict the angle. Yeah, so you have to actually restrict, because otherwise you have the sine and the cosine, which would have infinitely many zeros. But if you restrict this phi to a finite interval, then it's a restricted analytic function. Cosine and sine are analytic, and then if you restrict it, then it's a restricted analytic. So you need these parts. And the exponential you need, obviously, because there's the exponential here.
Can C be equal to 2 pi just?
Sure.
And why this is not enough? I would say just consider 2 pi, and that's for all application it should be enough, isn't it?
Why do you say that? I mean, you mean in applications, maybe.
It's a complex plane, and that's what it is. So why do you need something more or something?
Yeah.
That's not what is this.
Yeah, no, you in principle you need much more, right? Because this set is huge, right? You have to, we know that in physics not only cosine and sine appear in some, so if you compute a Feynman integral, there are very complicated functions, some hypergeometric functions appearing. And you need more structure than just this.
If you push this C, the bigger C, you recover those more structures.
No.
Why don't consider just 2 pi?
No, you can do that for an example, but it doesn't. No, you have to include all the possible C's, and this is the. Okay, but so now there are also functions which are not tame and which you know from your everyday experience. So first of all, the gamma function is not tame. Gamma function, if you look at the interval from 0 to infinity, it's not tame. You don't see that, but it's true. Okay, the zeta function is not tame. The arrow function is not tame. So there are non-tame functions which are not in this structure. Okay. Okay, very good. Now, there is much more to say. There is a higher dimensional story. There are many theorems in higher dimensions which are very deep. The point, what I want to make, that is tameness is used as a property, right? You show tameness and then you combine it with something else in many recent proofs of deep mathematical conjectures. I just list some here. Feel free to look into the literature. These are very recent works. I didn't put the publishing date, so this is not even in the journal yet, but they are very recent works. So it's a very active field connecting logic, number theory, and geometry. So how is tameness at work in simple physical settings? Well, first of all, let me quickly explain what happens if you lower a cutoff. Let's now imagine that I have a field space which is a tame manifold and a potential which is tame. Then if I integrate out classically heavy fields, then I get a differential kind of this constraint restricting to the minima. And I have, since this is a tame function, you can show that its derivative is a tame function, and the intersection of two tame sets is by definition a tame set. That's part of the structure. And therefore, the vacuum manifold is also tame. Yes? Now, let us assert that the field space is a tame manifold. Yeah. So this is an assertion here. Okay. And then if you restrict to the VAFs, it's also tameness is preserved because this projection property, because of this rejection. So tameness is classically preserved when lowering the cutoff, and now what is happening when you go to the quantum level? Now, if you make this assumption, already things are starting to be ruled out, right? For example, my assumption that the potential is tame rules out such potentials which put your minimum into like an infinite spiral. Yeah. So this is not a tame potential when you kind of can infinitely spiral, and you see, well, if you make a linear projection, it has infinitely many minima. Another example is there are infinitely many vacuum compatible with you can never have infinitely many vacuum compatible with tameness. Yeah, so there are some string theory settings which you can immediately think, oh, there must be some sort of cutoff where the theory breaks down. So many functions do not appear, as particularly the function which I showed you in the very beginning with this kind of highly oscillatory behavior. And this was discussed in the early 2000s, and then people actually, these authors actually try to argue, well, maybe we should count these vacua as being the same vacua, that you can tunnel between them. No, if tameness is true, you just can't, this does not exist. This does not happen in the theory of quantum gravity. Yes?
So does this use this restricted setup? Where you have functions that just restrict to an area where they're not theoretic? Because then you would have to just cut this off and it would be tame, right?
Yeah, as soon as you, well, but this is really when you go to zero. Yeah. So if you cut it off phi, then of course these are tame potentials. So really, if you go to infinity.
So this does not use the like restricted ones.
Sorry. So this does not use you had this various function space that you looked at. This uses one of the exponential ones.
No. It's true in all of them. It's generally true. So I mean, if you look at this, say, phi going to 0, then actually you're probing the infinite line, right? Phi going to 0 goes to infinity. So it's the sign of you get infinitely many minima. And this is never tame in any structure.
Then I probably didn't understand this restricted thing that you did, because there it seemed like you can restrict to any part of your.
So it's always a combination on what is the manifold your function is defined on. If I look at the function on R, then this function, or here it's even the interval, right, from 0 to pi, or from 0 to c, then actually had infinitely minima because there's this accumulation point.
So you can only restrict in the complex plane. You never restrict.
No, but the problem is that sine of phi to the -1 is not an analytic function which you can restrict to this interval. On this interval, it's not analytic, not restricted analytic. Yeah.
Excuse me, I'm probably missing a point. So if you take a string theory, you compactify it somewhere, you claim that such potential never appear.
Yes. You're not missing the point, yes. I will show you why, indeed why. Yes?
So you said a few times that you don't like the sine function. It's fine. But I'm quite happy giving the sine function as a quantum mechanics problem and finding a band gap. So what are we saying here? That we shouldn't do condensed matter as an effective theory, or?
No, well, it depends on, you have to understand these models precisely. So first, you have to understand we will come to this, like the Sine-Gordon model or something like this, right? You have to say that whether or not your field actually lives on the real line, or if you kind of look at configurations which are just on a restricted interval. So the non-decider, sorry, but now I switch to, the non-tameness comes from the fact that you're looking at it at the real line. If you have some sort of cutoff to this, then it's fine. Yeah. So I'm not anti-sine. Yeah. So I'm fine with the sine function as long as it lives on an Exactly. Yeah. And I think this is, by the way, what one does in practice in physics all the time. So you will see that much of this feels very natural if you think about this. But this gives kind of a mathematical formulation of this, and then you can use it. Okay. So then there was some fun paper appearing which invented a QFT with a scalar potential which has its undecidable statements. So you were not able to decide whether the theory preserve supersymmetry or break supersymmetry? Well, if you look at it, the scalar potential which appears there is not tame. Yeah, this ties into this connection with logic and decidability. Okay, now I should, how do I do with time? I should hurry up a bit. So I should tell you now evidence of tameness. It's very important to explain you the structure properly, otherwise it's just words. So we lost quite some time. So let's look at some evidence from string theory. So the first thing is, let's look at theories which have a lot of supersymmetry. Scalar field spaces, which are these coset spaces. Yeah? So if you have a lot of supersymmetry, the scalar, well, lot, I mean bigger than 2 in 4 dimensions, then the scalar field space is this coset space. Of course, we have heard this in this conference before, where gamma is some discrete symmetry group that is gauged. Yeah, so it's divided out, so it's not, it's gauged. Okay, we call it coset space. In mathematics, you would call it arithmetic quotients if this gamma is in arithmetic groups. So in fact, it was recently shown in this seminal paper that these scalar field spaces actually admit a tame structure. So they are actually tame manifolds. What does that mean? That means that you can cover them by finitely many charts, okay? And that all the transition functions from one chart to the other are in fact tame functions. Okay? In fact, they are already tame in this structure R-alg, so in the polynomial structure. It's maybe not too surprising. So in higher supersymmetric theories, you don't have instanton corrections. You don't need the exponential function. Okay? So they are tame in this structure if this gamma, this discrete group, is sufficiently large. Yeah? And this was shown in this seminal paper. In fact, they construct the charts explicitly, which are known as Siegel sets. Now, what about the coupling functions? The coupling functions are now, for example, the metric on these manifolds and so on. And in fact, you can also show, that's what we will do at the gauge coupling function, that they are tame functions in this R-alg structure. Now, is this a general, so now the field spaces and the coupling function at 2 derivative level in this higher supersymmetric theories are tame. These are non-trivial results, by the way. So it's not, these are not obvious, these, by no means, these theorems. And the remaining question is, are the parameter spaces tame? Yeah, what are the parameter spaces? Well, the spectrum and the gauge groups, for example. And now you have to show that they are finite when they come from a quantum gravity theory. So that's where really supergravity is different from a theory which comes from string theory. In supergravity, you can construct infinitely many groups. Yeah, you can just put more and more vector multiplets, for example. But in string theory, this seems to be not possible. And that's what these papers talk about, which I cited in the very beginning. They tell you you can never get 1 million vector multiplets.
Well, excuse me, do you suppose it, or this is just inherent feature of string theory, that string theory is like that it never appears?
No, that's what the evidence from string theory shows, what these papers try to show. So they try to find argument why there are cutoffs at the number of vector multiplets, for example, which you can get from a string any string compactification. There's a lot of effort focusing on this. Yeah. And then, if this is true, then tameness also of the parameter space can be true. So because infinite discrete things are never tame. Yeah, that's what was the point in this one-dimensional set. Okay, so that's the setting under higher supersymmetric. So now let's go to lesser supersymmetry. Calabi-Yau compactifications. If you look at Calabi-Yau compactification, you get n equals 2 theories in 4 dimensions. And we can compute the Keller metric, the metric on the moduli space, and the gauge coupling function. And the important fact is that they are all derived from one underlying set of functions which are so-called period integrals, what are period integrals? Period integrals are the integrals over the 3-0 form in Calabi-Yau threefolds, and they are very non-trivial transcendental functions of the complex structure moduli. Okay. Now, how can this possibly be tame? Well, we have to use another remarkable result from this recent paper. Namely, this paper shows that actually all of these period integrals are tame functions. Yeah? Or at least the period map are tame, and then you can even show that the period integrals themselves are tame. Okay. In fact, now you need this whole structure. So you really need the exponential. Obviously, there are instanton corrections or exponential corrections. And there you need the restricted analytic because there are cosines, there are hypergeometric functions. There's really complicated functions appearing there. So we see that tameness is preserved in this case. There might be, again, parameters. And if you want to show that the parameter space is tame, you need to show that there are only finitely many choices for these parameters. One important thing you would need is, for example, you would need the finiteness of Calabi-Yau manifolds, which is claimed to be true, compact Calabi-Yau manifolds. Okay, now, so far I only told you examples where coupling functions are tame and where field spaces are tame, but you can show even, and that's what this our general theorem is about, you can even show that parameter spaces can be tame, or have to be tame when they come from string theory. If we look at these flux compactifications, which are really well understood, which have these vacuum conditions, you can show that the scalar potential is a tame function. So it has only finitely many minima if you fix the flux. But if you keep G4, the flux, as a parameter, you first think, oh my God, I now lose tameness because this is an infinite discrete thing. It lives on a lattice. It's the worst thing for tameness. But there's the tadpole condition which rescues you, which is kind of a global consistency condition for compactification. And then, in fact, you find that if you take this into account, tameness is restored, even as a function of these discrete parameters, if you restrict them by the flux. And this is a generalization of parts of a very famous theorem on so-called Hodge classes. Now, in the last few minutes, let me give you some evidence from quantum field theory. So this is something very exciting, which I'm very excited about at the moment. Namely, if you look at a general L-loop amplitude in a quantum field theory, which is, let's say it's renormalizable, then that amplitude I can think of as a map from the space of momenta, and the parameters are masses and vertices. And what we show is that these maps are actually tame functions. So now, while these period integrals were holomorphic, so you could also say, oh, this has something to do with holomorphicity and so on. These are real functions. These are general real functions. And what one shows is that they are also still definable or still tame in this space. So how does this work? So one important fact is that every amplitude can be composed of finitely many Feynman diagrams. And then every Feynman diagram can be built from finitely many master integrals. So you need quite some heavy results from Feynman amplitudes. And then you have to use the fact that these Feynman integrals, these master integrals, can be related to period integrals. So this is always our main tool. So you construct an auxiliary geometry, and you show that these Feynman integrals are actually appearing as period integrals in this auxiliary compact geometry. Yeah. So I don't have time. I'm anyway late already. I refer you to a book by Weinziel, for example. This is something which is studied by many people working on Feynman amplitudes on the mathematical side. And so there's a lot of literature on this. Now, we can use the fact that period integrals have recently been shown to be tame by themselves. And therefore, also, we can use then the projection property to say that the Feynman amplitudes, that these loop amplitudes are tame. Yeah. Well, if you go to the non-perturbative level, our sine function or cosine function comes into the game again. You have instanton corrections. So what do I do with this? So now we have periodic things. Well, if I use this periodicity as a gauge symmetry, then I can save this. And this is exactly what happened here in these coset spaces. So if this gamma is sufficiently large, if you mod out this symmetry, this discrete symmetry group, then these functions can be tame. So the sine function, if you just restrict it to the interval, is tame. And this is related to the idea that in a quantum gravity theory, you don't have global symmetries. Yeah? So discrete global symmetries should not be. Now, that's not the end of the story. Actually, try to check now. What we did is we looked through the literature wherever we found results about non-perturbative results about quantum field theory. We checked if there is tameness, and in fact, these are few examples. So in 0 dimensions, we found Sine-Gordon that this can be related to periods. It's tame. In these 2D theories, in 2D string theories, and admittedly, where does our power come from? We usually relate things to period integrals. And even in integrability, that's something important to, very powerful to do. Yeah. That's where we get this from, because tameness is not easy to check by any means. Yeah. So if I look at the function, you cannot easily see if it is tame or not. You can see if it is non-tame if there are infinitely many zeros, for example. And finally, in the last 3 minutes, I wanted to tell you a little bit evidence from this deformed Wessel-Witten model. So I can skip this. So you start with a Wessel-Witten model, and you gauge the diagonal subgroup, which is this G over G model. And then there was, I think in 2014 or something, like by Svetzer's, a kind of a deformation introduced, which turns this into a much more interesting model because it has a non-trivial, can have a non-trivial field type, one of these deformations. And then it's still an integrable model with some classical conformal symmetry. And here are its equations of motions if you rewrite them in an appropriate form. And what I'm now claiming is that also the solution, or at least a certain set of these solutions, are in fact tame. Yeah? So the solutions are actually tame. Now, the solutions can be horribly complicated. So how can we possibly see that they are tame? Well, we again relate them to periods. So we relate them to these deep theorems. And how do we do that? We take an ansatz for G and A, where Q is some complex Lie algebra element. And if we consider this Lie algebra element to be of this type, namely that it bars to minus itself, and I pick beta of this form, then G is actually real. Yeah, it's element of the real group G. And then I can interpret the solutions to this deformed sigma model as coming from an auxiliary variation of Hodge structure, an auxiliary Hodge structure. So in fact, such an operator would be called in mathematics a grading operator. Okay, and it splits your vector space, some auxiliary vector space, into eigenspaces. Okay, and this is exactly what one calls a Hodge decomposition in mathematics. So the solutions to the sigma model are actually of this type. They are actually given by Hodge decompositions.
All of the solutions?
I'm not sure. I don't think all of the solutions. Yeah. But I will come to this in a moment. Okay. Now, what is actually this G in this case? Well, it's actually the Hodge star operator on this auxiliary geometry. So it's pretty remarkable that in this setting, then we are now back to the geometric setting we used in all of these string compactifications. So now, do the solutions correspond to a variation of Hodge structure? Then they would be period maps. And in fact, you can check that, and you see that if I pick the parameters in this way, in fact, there are good reasons for picking them this way, then they are indeed defining a variation on Hodge structure. This is technically more involved. Jeroen is around. Please ask him questions if you're interested. Okay, so there's a lot of technical stuff here. In fact, you find that exactly the equations of motions reduce to the equations of which define a variation of Hodge structure. So in other words, the sigma model, the solutions, if you supply boundary conditions, in fact, to the monodromy, you find that they are, in fact, these period maps. So the solutions are period maps, and the period maps are tame. And yes? As far as we understand, yes. At the moment, yes, but I will come to this in a moment. So the solutions are period mapped, and now we are in a set of 50 years of heavy mathematics and results, which you can all use to study the solutions to the setting. And in fact, for example, you can look at asymptotic solutions near punctures, and they tell you a formalism how to get them. Very, very non-trivial, but can be done in explicit examples. There are infinite recursion relations, which can be solved by the ingenious of these mathematicians. Very famous paper, actually. And there is also a classification of all possible solutions, or all possible type of such things. This is more recent. Okay. Now, how far can we develop this? And now it comes to the question which I was asked 2 times, namely, are the other deformations also part of this? Well, my feeling is that we are just at the tip of the iceberg. In fact, we are just talking about Hodge structure, but there is a huge field of mixed Hodge structures which has more degrees of freedom. And I suspect that many more of these integrable models or solutions to these integrable models are actually what is called mixed period maps. And then you can use the method. So this brings me to the end. It leads me to say that there is a natural tameness conjecture that, in fact, scalar field spaces, parameter space, and coupling functions in any theory which comes out of quantum gravity are actually tame. It's a bold conjecture, but maybe it's true. I didn't find a counterexample yet. And my conclusion, I leave them to here for you. I think it's amazing to see that one finally has a structure, or a potential structure, for the real world. And with real world, I mean not so closely tied to holomorphicity or something, but still can lead you to interesting result. And it appears in quantum field theory, it appears in some relations to integrability, and it has even connection to some other of these recent conjectures about theories from quantum gravity. Thank you, and sorry for running over time a little bit.
Yeah, thank you, Thomas, for the nice talk. So we still have time for a few questions.
It's just a question. The mathematician working on the variation of Hodge structure, they knew that their equations are integrable?
Yes.
Yeah, they knew it.
Yeah. So, yeah, I don't know about the history about all of these things. So my feeling is that in these mathematics papers, so the Nahm's equation appears. They realized that Nahm's equation comes out in this 80, now even in the 70-something paper by Schmidt. So they realized that these equations come out, and then there was this development by Hitchin at the same time. But you have to realize that they really develop in these works very nicely usable formalisms to solve this. Maybe this is something which appears in physics in a different reincarnation, but I'm not sure about this. So this kind of infinite iteration to solve these equations is pretty remarkable. And if you do it once, it's amazing that it works out. And it works for any group, so it's completely general. It's not what one sometimes does in physics. You start with SU2 or your favorite group. They tell you using group theory. It's all group theory and some heavy linear algebra. They tell you how to decompose these groups and how to reduce these things. And it's one, we spend a lot of time on this paper, and it's very fun to read them because you realize they're very computational. They're not like papers about categories or something like this. They're things which you can actually, I don't want to diss categories, but you can actually compute things using this. Okay.
Just opening a speculation, how powerful is tameness in the sense, holomorphicity we know is extremely powerful. Think of Seiberg-Witten theory, which presumably is tame because there's period integrals. Is there constraints that you can put on potentials through tameness in the same sort of way?
Yep. Yeah, so the remarkable thing is, and I've hidden this because, of course, that's something very exciting, but I don't have much to say about yet. Tameness becomes very powerful if you combine it, say, with analyticity. So you can hope that if you combine it, so say you have some Feynman integrals and you have that they are tame. If you combine this with and that's what these mathematicians are actually after, is if you combine that with analyticity, then you can find new algebraic relations. So it's actually very powerful, and much of the, when you talk about Seiberg-Witten theory, what the people doing Hodge theory realized is that with this kind of connection to tameness, you get this behavior near the singularities. This is actually a tame behavior, and this tame behavior is actually so restrictive that it already tells you what precisely can happen to some extent. So if you hear some of the talks also by my collaborators, they say like, oh, many of these local theorems which tell you what happens when you go, say, to the monopole or in conifold points, say, is actually captured by the fact that these periods are tame, or the Seiberg-Witten periods are tame. And, yeah.
Is there any extra structure in this tameness field which is not necessary for physics? So is this something that we could further restrict and reduce tameness?
Yeah, that's a good question. So what I'm not sure is, what is the, you can ask a valid question is, what is the right tame structure to use? Should I go as big as possible? So should I use the biggest tame structure which you possibly can construct, which is maybe not even known, yeah? So I used always this R un exp, which has the exponential function and the restricted analytic. But they are more sophisticated structures. And maybe in physics, actually, you have to pick a very clever tame structure, which is then the suitable for your setting. So indeed, there could be something which is too much, which you have to restrict away in the most general structure.
Related to your point about tameness on non-perturbative level. So in 4 dimensions, we have kind of unique source of functions which come from localization. In particular, all sorts of Bessel functions. Some Bessel functions are probably not tame.
Yes, that's true.
But in general, it would be interesting to check that.
Yeah.
So just matrix models.
Right. Yeah. So partly we look at this. So in particular, like if you have a tame potential and you have localization, then you can hope that tameness is also preserved for the partition function. So that's an argument which we will present. And we look at a few examples. Mike, of course, knows these settings very well. So we dig through the literature. Unfortunately, it's not from the mathematics side. If I give you some Bessel function, for example, for this zero-dimensional phi to the 4 theory, there's also, I think, a Bessel function coming out. And it has the right asymptotic to be tame, but we cannot prove that it's tame. That's why I wrote likely. So indeed, there are Bessel functions which are periodic, And they cannot be tamed, but all the things which we checked actually turn out to be the ones which have this nice asymptote. By the way, it's also the asymptotes which you have in string theory, like in these kind of exponentially falling off asymptotics of Veneziano amplitudes and so on. It's very curious. And even there, I cannot answer the question whether or not this is a tame function. I'm repeating another question which I got before. Are string amplitudes tame? I cannot answer this. So this is the tricky thing. Don't throw a function at me and ask me if it is tame, because it can be really complicated to say yes or no. Yeah. Like with the Bessel function. Okay.
Yes. So if I understood it correctly, so indirectly you define something like tame manifold and tame Riemannian structure. And so this structure is somehow friendly, that, for example, if you calculate the Ricci scalar, it is bounded or something like that. Or
So in tame geometry, in tame differential geometry, there are very well-known papers about the boundedness of gradients. So and that's why. Yeah.
so basically, yes.
Basically, there are some results on this.
Yes.
Yes. Of course, I have to tell you more details, but that's also one of the reasons why this is or minimal structure are popular in machine learning, for example. So you can ask in machine learning what are good functions as activation functions, and then tame functions are a good set of functions because they have certain nice properties, kind of convergence properties also of these gradients, steeper descent and so on. Don't fully understand that, but I've seen a lot of interest in these kind of inequalities. I don't know the name of these Kudoika inequalities. These are very well-known inequalities.
Okay, Thomas, thank you very much again.
There was another question. But
there's another question. Yeah.
Is it all right, just quickly? Is there some connection between the functions that are appearing and the functions that appear in Borel resumability and resurgence? It looks similar. I mean, there are some.
Yeah. I know.
Please.
Yes. So this is something which we started to read only recently. It looks very intriguing. I fully agree on this. Yeah. I cannot say yes or no, but it seems very intriguing to think about it this way.
Okay, thanks again, and we will have. We'll have a coffee break, and we'll be back at 12. Okay. Hey, everybody. So nice to see you all back here. It's nice to have Chris Blair with us today virtually. Hi, Chris. So, and Chris will tell us something about generalized usual solutions and supergravity. Please, Chris, go ahead.
Okay, thank you. So first I should start with a very big thanks to the organizers, not just for inviting me, but for accommodating it so that I can speak to you from afar today, and for already putting in the effort of making everything available online. So it's a big effort, and I appreciate it. And I'm sorry I made it more difficult, and I'm not there in person. But I think hopefully I can give the same sort of talk I would have given anyway, and hopefully it will be clear and no technical difficulties. So I'm going to talk about I'm going to sort of summarize the results of 3 papers from the last couple of years, 2 with my PhD student Sophia here in Brussels, and 1 also with Dan, who's at the conference. And the topic is about so-called generalized duality, and I'll try to explain what this idea is. So I'll start with a very anodyne statement, which is that in this conference and in string and M theory in general, duality is an important central connecting principle that allows us to explore different parts of the theory, find new solutions, and draw links between different topics and different behaviors. And my talk today is really going to focus on duality as something of interest in itself. There'll be little bits of mentions of deformations and a much less mention of integrability. But there will be things that I think will be of interest and which will speak to the other topics of the conference. So in particular, the type of duality which I'm going to talk about is masquerading under the name of generalized dualities. So the precise sense in which it's a generalization of, let's say, standard string theory dualities will become clearer in a couple of slides, hopefully. But I talk a little bit about the motivation for studying this topic in general. So generalized T-duality will probably be more familiar to people in the audience and will be the subject of other talks at this workshop. And it's of interest as a mechanism that generates new supergravity solutions. Non-abelian T-duality is an example of a generalized T-duality, and it's led to a lot of work in constructing new interesting holographic backgrounds. And generalized T-dualities have a lot of links to integrable deformations of worldsheet models and backgrounds leading to these integrable theories. So it's kind of a tool that you can use to explore and find new interesting string theory backgrounds. From a more mathematical point of view, perhaps something that's also of interest to me and maybe coming from this doubled and exceptional geometry community is that to make the structures that appear in generalized T-duality clearer, you find out that you have to look for, emphasize the role of underlying doubled geometric or doubled algebraic symmetry structures. So these are dualities that on the face of it may seem a bit obscure when you first meet them, but which look cleaner from a different perspective, which uses these powerful duality symmetric structures. So generalized T-duality is pretty well established and is being used extensively. So T-duality is a famous symmetry of string theory in 10 dimensions. But we know that there's this non-perturbative extension, which is U-duality, which then applies also as a duality in M theory in 11 dimensions as well. So recently there's been some work about trying to come up with definitions or frameworks in which you could realize generalizations of the U-duality symmetry that look like these known forms of generalized T-duality. So why would you want to do that? The first reason I came up with is just to see if it exists. Often structures in string theory have some nice lift or generalization to structures in M theory. So first of all, we want to know if you can actually define other sorts of generalized dualities that would apply in that context. And then, okay, assuming it does exist and is useful, what you want to do is then try to repeat the successes of generalized T-duality as a probe of the sorts of, as a probe of interesting new supergravity solutions in both 10 and 11 dimensions, and then to see if you can find solutions with properties related to holography or interesting integrable or otherwise deformations, to see if you can find solutions with similar properties in 11 rather than 10 dimensions. And then again, from maybe my personal perspective, it's also interesting because the sort of common feature that I'll leverage to define generalized U-duality is to look at these sort of underlying doubled or exceptional geometric symmetry structures, which pop up and new structures appear that are sort of interesting to study as features of special supergravity solutions that you can then use to define notions of generalized U-duality. So that's the sort of slightly big picture motivation. And the actual result, which will come out of this motivation in this talk, is the following. It's going to be what I'll describe as an example of a generalized U-duality, and it will be a sort of elaboration of non-abelian T-duality, which is perhaps the most well-known generalized T-duality. So non-abelian T-duality is a duality transformation between a space that has non-abelian isometries to a dual background that has fewer isometries than the space you started off with. So here's a sort of standard example. You start off with the three sphere, regarded as the group manifold SU2. You do a dualization procedure and you get a non-abelian T-dual background that in a certain sense has abelian non-isometries, meaning that if you tried to look at the commuting algebra of the would-be algebra of translations in this background, translations are not a symmetry. You don't have a translational isometry, but the isometry is broken in a very specific way thanks to the presence of some dual Lie algebraic structure. So there's some rigid symmetry structure underlying the form of this dual background, which is inherited from the non-abelian symmetry you started with. And I'm going to describe an elaboration, which is a similar map, but in the context of an 11-dimensional, something that will generate a solution of 11-dimensional rather than 10-dimensional supergravity. And it's actually going to be a map, not from a space with non-abelian isometries, but from a three-sphere in type 2a with an SNS flux to an 11-dimensional background, which will have a similar appearance to the non-abelian T-dual background that you get from non-abelian T-duality, but where the sort of rigid algebraic structure that's preventing you from having certain translational isometries is not connected to a Lie algebra, but to a tree algebra structure. And this is a generalization of this non-abelian T-dual chain, but it's slightly different in spirit. So a little piece of intuition from regular T and U duality is that T-duality can swap between 2B and 2A. So a single T-duality does that, or any odd number of T-dualities. Whereas U-duality sort of keeps you in 11 dimensions, or keeps you in 2A, or keeps you in 2B. It can only reduce to an even number of T-dualities. So even though on the right-hand side I have some structure similar to the non-abelian T-dual, I don't quite see non-abelian isometries playing the same role. And what I think I'm really going to describe to you is a generalization of a T-duality chain where if I take this tree sphere and I do a T-duality on the hop fiber, I get a space which is S2 times S1 with flux. And we should really think of the generalized U-duality I described to you today as generalizing a map from this S2 times S1 with flux to this non-abelian T-dual background, skipping this middle step. And this is what's going to get uplifted to this U-duality elaboration. So I'll explain later on why I decide to sort of, I don't focus on the non-abelian isometries so much. I focus on the structure of the background that appears on the very right-hand side of these chains. And okay, the motivation for doing this I will come to later, but the upshot is this mechanism is a solution generating mechanism between 10-dimensional and 11-dimensional supergravity. And I claim it gives interesting 11D backgrounds. So in a paper this March, we studied some examples. So I have a duality or a set of rules for taking a solution of 10-dimensional 2A supergravity of the form M7 times a 3-sphere. I chop off the 3-sphere and I replace it with some new 4-dimensional space by a generalized U-duality transformation, and I get a new 11D solution. So an example would be if this spectator 7-dimensional manifold is ADS3 times T4, in which case I can view my initial solution as a near horizon of a string 5-brane intersection. Then I get an 11-dimensional ADS3 solution, which actually turned out not to be a new solution, but it fits into a class of ADS3 solutions that has been obtained a couple of years ago. And what's interesting about this fact is that the solutions my procedure generates are all local solutions. You don't know the global range of the coordinates that you write down the solution in. But these ADS3 solutions that have been already studied have there's a prescription to give them a global completion using ideas from holography that are very similar to what appears when you study non-abelian T-duality. So this new 11D solution, which shares features with non-abelian T-duality, also shares some of the features of the holography and global issues of non-abelian T-dual solutions. Then in this paper, we also could consider the case where this initial solution is this string 5-brane intersection. And you can look at just the 5-brane near horizon region. In fact, we always have to do that. And then this more full solution can be viewed as a particular deformation of this ADS3 limit. It's a kind of weird deformation. It's what I've called a 6-vector deformation. So it's actually a deformation by an element of the U-duality group, but not acting on isometric directions only. It acts on both 2 isometric directions and the 4 special directions of this new space, which are not isometries. So it's an unusual deformation, and it takes you basically away from the near horizon region of the string to this solution. It's in fact inherited from TST or bivector deformation of the original ADS3 times T4 solution in 2A. And I just mentioned that has a holographic interpretation has been dual to the TT bar deformation, version of the TT bar deformation of the dual C of 2. So that's an interesting link there, about which I will not be able to say very much in this talk, but I mentioned it as it should be interesting. And in fact, a more general statement about these deformations is that if I take this solution generating mechanism and I suppose that the spectator 7-dimensional spacetime has 2 commuting isometries, then in string theory I can consider doing particular T-duality valued deformations, such as TST deformations. And any such deformation is inherited by the new 11-dimensional solution as what I call, again, a non-isometric U-duality, particular E6 U-duality valued deformation of the 11-dimensional solution, which acts in both isometric and non-isometric directions. And this seems to me to be an example of a new class of potential deformations you can apply to particular solutions in supergravity, those that come out of these generalized duality constructions, where you're doing something that's like a U-duality, but you're not relying on isometries, which you should normally do to apply U-duality. So that basically completes, I think, what I would call the gong show version of this talk. So a little summary of the motivation and a little summary of the results. So if you don't like listening to remote talks at physical conferences, you can now switch off and go for a walk. I can't really see you, so I don't mind. And so what I'll now do is I'll sort of go back and elaborate on the introduction and the motivation, and try to be a bit more clear about what I mean by generalized U-duality, or how I could formulate generalized duality in general. And after I'm doing that, I'll talk about these results again in a slightly more technical way. But I just leave a little pause in case there are any questions so far. Okay. And so now I'm going to go back to the beginning, or the motivation, and start thinking about duality. So the generalized dualities I'm talking about are generalizations of this, of the classic string theory or M theory dualities, which are usually phrased as a relationship between two different theories on different backgrounds. So theory 1 on some spacetime M times x1 is dual to theory 2 on space M times x2. And the classic T and U dualities, these apply when the spaces x1 and x2 are tori or have abelian isometries. And this is a large part of the duality web of string theory uses these dualities to relate type 2 on a circle with type 2 on a dual circle, and so on and so forth. So one question is, okay, how can you generalize this away from, let's say, away from tori? And I'm interested in generalizing in a sort of systematic way. So you can certainly think of many examples involving spaces like K3 or so on. But I want to look for things that are similar in spirit to T and U dualities, where I have some prescription to identify classes of spaces X1, which lead to classes of spaces X2. And I have some nice set of transformation rules between them, akin to the Bush rules in T duality, for instance. So given that the basic requirement for T duality or U duality is that you have some abelian isometry, a starting point would be to say, well, what happens if I apply duality in a situation where I have isometries, but they're non-abelian? And I can most easily do this in T duality, because then I can use the worldsheet sigma model to apply such dualization procedures. And this was done long ago for the case of non-abelian T duality, where you carry out a similar dualization procedure as you do for ordinary T duality, but in a background with non-abelian isometries. And the interesting feature is that you get a dual background, but you kind of end up with a dual background that's not of the same type as you started with. So you end up with a background generically with fewer isometries than the initial background with non-abelian isometries. If you start with a group manifold, you end up with something that's not a group manifold. So what this tells you is that isometries are somehow not the essential ingredient in whatever class of generalized dualities this is beginning to construct. And this is made really manifest when you then turn to what turns out to be a more general case of generalized T dualities, which is the Poissonly T duality. And this relates pairs of dual backgrounds which are specified by an underlying symmetry structure that's not actually a symmetry of the spacetime itself. So there's some underlying Poissonly group, which is just an ordinary group, but with a little bit of extra structure in the sense that you can define a geometric object called a bivector. So something with two vector indices on the group obeying certain compatibility conditions. And there's a particular relationship between the spacetime geometry and the data on this group. But the action of the group is not an isometry as long as this bivector is non-zero. So there's some additional information contained in this extra object related to a dual Lie algebraic structure. And this appears in this more general Poissonly T duality, which gives you pairs of classically canonically equivalent to a dual sigma models. But there's no real role being played by a space-time isometry, but there is a very important role being played by a more intricate and somewhat more hidden symmetry structure. So that's a starting point for studying generalized T duality. Then if you wanted to ask similar questions in the U duality case, well, you can't rely on worldsheet sigma model approaches. This is because whereas T duality is perturbative symmetry, relating strings to strings, U duality is non-perturbative, it relates strings to branes. So already you need, well, additional angles, or you need additional evidence to understand U duality and its relationship to T duality. And the generalized T dualities, which I described in the last slide, it's already a bit unclear what happens when you want to extend to the full quantum string theory. You get a little bit less information from the worldsheet theory than you get in the case of T duality, where everything is sort of under control at the quantum level. So For U-duality, you don't even have a world sheet or world volume model that you can control. So what's safest to do is what I'm going to do next is restrict to supergravity. You can formulate these generalized T-duality transformations at the level of supergravity. And then it's clear how to generalize to 11-dimensional supergravity and interpret in terms of U-duality or generalized T-duality. So in the supergravity setup, and the justification for this restriction is also that, well, this is sort of where these transformations are known to be useful as solution generating mechanisms. So even if I can't answer questions about whether it's an honest or full duality in string theory, M theory, at least I'm going to get something I can use pragmatically in supergravity, which is nice to have as well. So in the supergravity setting, I'm going to slightly rephrase my statements about duality. So previously I said, oh, well, theory 1 on space x1 is dual to theory 2 on space x2. And the word on is doing a lot of heavy lifting in that statement. So another way of describing the relationship between two theories which are dual, which is often used in string theory as well, is to think about it in terms of a dimensional reduction. So if I dimensionally reduce theory 1 on x1, and I dimensionally reduce theory 2 on x2, these theories will be dual if what I get at the bottom is a common theory defined on this common spectator spacetime now. So for instance, type 2a string theory on a dimensionally reduced on a circle, or a type 2a supergravity dimensionally reduced on a circle, gives you the common 9-dimensional maximal supergravity, and you also get that from a dimensional reduction of type 2b in a circle. Then you have to do some fields relabeling in 9 dimensions to relate these two reductions, and that's equivalent to doing duality in 10 dimensions. So all ordinary string dualities in supergravity, I can think of them in this way, in terms of a reduction to a common theory from two slightly different starting points. And so my definition of duality can be this statement, and this is now a slightly weaker statement, that I do some reduction or truncation of the two theories, I get the same theory. And that's useful in supergravity if it gives me a way to take a solution of the first theory, reduce it to a solution of the common theory, and then invert the reduction procedure by uplifting it to a solution of the second theory. So I can do this if I know I can map solutions from higher dimensions to lower dimensions, i.e. if my reduction is a consistent truncation. So I sort of have a commutative diagram of sorts where, okay, my solutions are dual if I can use this procedure to go from one to the other. And once I've done this, I can sort of forget about the lower dimensional theory. I can just write down what were the rules to take the solution of the first form, m times x1, to a solution of the second form, m times x2. And that uses as a technical tool the common theory in lower dimensions, but at the end of the day, I can just say, okay, here are the rules to go from solution 1 to solution 2. So for this talk, this is kind of what I have in mind as my definition of generalized duality. It's kind of broad, but I'd say it's a very weak notion of duality. So this is certainly a solution generating mechanism. If I have two backgrounds and I can consistently truncate them to the same solution in lower dimensions of the same lower dimensional theory, then I have a map between the solutions, and I can regard that as a solution generating mechanism or as a generalized duality. This certainly includes known dualities and known generalized dualities as examples. Let me say at this point that then if you view this just as a solution generating mechanism, maybe you object to calling it generalized duality. Maybe duality is a stronger word, but okay. That's kind of a question of language. So as a first step towards formulating these dualities, at least I'm setting up this solution generating mechanism. So then also, what I described is also very general. That means it needs to be useful as well as general. So for truly to be useful, you need a recipe for identifying when you have this setup with pairs of dual backgrounds. and this sort of recipe is what sort of comes with known formulations of generalized T-duality. It's why they're useful. It's quite clear when they can be applied. This general definition is much more general, but you have to sort of then be precise about what sort of rules are in place to ensure that you can do this mechanism. Something which helps here is the question of how do you identify, given some upstairs space and you do this truncation, what is the lower dimensional common theory? So in the examples of generalized dualities that I described, the lower dimensional common theory will always be a lower dimensional gauge supergravity. And so this is some extension of the ordinary supergravity where you have some local non-abelian symmetry with so-called gaugings or structure constants, which I denote by capital F. And the algebra of these structure constants will pop up again, or is also going to be some special algebras that will underlie known notions and new notions of generalized duality. So this is the framework in which I try to set up now some definition of generalized duality. And so what I try to focus on is with this idea in mind of having different backgrounds that reduce to solutions of a lower dimensional theory, the same solutions. What's the recipe for knowing when you can do that? So I'll start by describing this recipe for the case of Poisson-Lie T-duality, which is a very well-known generalized T-duality. So I alluded to this earlier. The data you need to specify this duality is a Poisson-Lie group, so some group manifold in which I have some bivector pi. So I have some compatibility conditions between the group and the bivector. And so I write down some differential equations here. So these L's are the left invariant one forms on the group. So L is trace G inverse 2G, or the other way around. They obey this Maurer-Cartan equation. And this bivector is meant to obey some condition like this. So in the equation here on the left, you have the structure constants for the Lie algebra of the group. And then the derivative of the bivector involves those structure constants, but also involves dual structure constants of tilde, which is some extra structure associated to this Poisson-Lie group. And there's different recipes for constructing the space-time background that admits this Poisson-Lie T-duality, or that is built using this data. So instead of giving you the explicit formulae, which are not illuminating on their own, I'll give you a less explicit formula, which is more illuminating for my purposes. And this is the prescription to embed these Poisson-Lie backgrounds in terms of generalized geometry. So here I want to describe the background in terms of the metric and the B field in 10 dimensions, or in some d-dimensional subspace of my full solution. And a useful object with which to describe the metric and the B field together is this 2D times 2D matrix, which I would call a generalized metric. And this is a nonlinear combination of G and B that has particular nice properties under ordinary T-duality and under dimensional reductions. But the particular form of the metric and B field for a background which emits Poisson-Lie T-duality follow from a factorization of this matrix, in which all of the data about this Poisson-Lie group factorizes out in this matrix E, which I should think of as some sort of generalized Vielbein for this combination of G and B, and some constant flat metric, which I denote H naught. And so appearing in this matrix E are my left invariant one forms L, their dual vectors V, and this bivector pi. And if you inverse this relationship with H naught, some arbitrary matrix constants obeying some ODD condition, you can extract explicit expressions for G and B in terms of L and pi, and these constants. And there's a special property of this factorization, which is important, which is that if I'm doing things in generalized geometry, I can formulate Okay, first of all, I can formulate a notion of a generalized vector, which is a pair here of a vector and a covector. And there's a generalization of the Lie derivative acting on such pairs called the generalized Lie derivative. And the inverse of this generalized Vielbein gives a basis for generalized vectors, which obey a sort of parallelization condition in which a particular set of structure constants appear related to the structure constants of the related to the structure constants I mentioned on the previous slide, which will control the form of the lower dimensional theory and which play a role in determining the allowed dualities in this setup. And so this condition generalizes, if I was just dealing with an ordinary group, these vectors VA would obey a parallelization condition that they're under the Lie derivative, they would form the Lie algebra of the Poisson group. But here I don't only have a group structure, I also have this bivector structure. And I guess a bigger 2D dimensional algebra associated to these backgrounds. So the generalized geometry, if you formulate it in terms of this particular set of variables, sees both f and f tilde, whereas if I structure this as a group manifold, I would just see f. So I have to work with additional structures. And the algebra that appears is known as the Drinfeld double algebra, and it incorporates both these structure constants f and these dual structure constants f tilde on the same footing. And this has some special properties, namely that there are two subalgebras. So this structure constants f give you a subalgebra, and the structure constants f tilde give you another subalgebra. And the statement of Poisson T duality at the algebraic level is just that you can swap this algebra T's with this algebra for the T tildes. It's equivalent to swapping f and f tilde. And then to generate a new background, you can go back to the differential conditions I wrote down on the previous slide and solve them with f and f tilde replaced, swapped for some new group data and a new bivector. And then you can build the same objects in generalized geometry, and you build a new background, new metric can be filled in this way, and that creates the rules for Poisson T duality. So the duality has a sort of geometric incarnation, which is slightly complicated, but this geometry encodes a particular algebra via the generalized geometric realization, and is also an algebraic incarnation of the duality as this exchanging subalgebras with special properties from one another. Now, a special case of this Poisson T duality is non-abelian T duality. So I focus on this a little bit because I want to specifically generalize this. So in the non-abelian T dual case, you start off with an ordinary group manifold, let's say. So that's a situation where I can forget about this confusing extra structure, the bivector, and I just have some space with some non-abelian isometries specified by non-zero structure constants f, a, b, c. But these dual structure constants are not present. And then the duality that I'm telling you exists, this swaps f and f tilde. And it gives you a structure then where your Poissonian group is trivial, it's abelian because your f's are 0. But there is a non-trivial bivector because you have these dual structure constants non-zero. And the condition that d pi is f tilde can be solved by taking your bivector to be linear in some new set of coordinates x, which are the coordinates on your new space. So a specific example is this example of S3 viewed as SC2. So if my initial metric on this S3 is just given by these left invariant forms, L tends to L, the non-abelian T-dual space comes out with if you go through the steps or figure out what these generalized metrics tell you about the background, it comes out as this three-dimensional background here. So this space then is not a group manifold in itself. It has a complicated structure, but it has quite a simple presentation as a Poisson group. It's defined by a linear bivector. And again, this space does not have the isometries that you started off with, and it has a a slightly curious structure. And one thing that's important is that both the metric and the B field get turned. So what I then want to do is think about what sort of versions of this duality could exist, not in string theory, but in an 11-dimensional setting with U-duality. And so in the Poisson-Lee setting, what was important was that there was this very specific group structure that then had a nice embedding into this generalized geometric construction from which you could extract the background and see things like this underlying algebra. And so there was a proposal in 2019, at the end of 2019, for what would be an analogous group structure that could control a version of Poisson-Lee U-duality. So the intuition here is that in 10 dimensions, you have a metric and a B field, which is a 2-form. And then in 11-dimensional supergravity, instead of having a 2-form, which couples to strings, you have a 3-form, which couples to membranes. And the idea of this generalization is basically to add an extra index to anything that is related to the 2-form. So the proposal of these people was that you should consider a generalization of a Poisson-Lee group where you don't have a bivector, but a trivector. The idea is that the bivector is in a certain sense linked to having a 2-form in your spacetime theory, and the trivector is now linked to having a 3-form in your spacetime theory. And you can then assume that the group is still a group, so you have this sort of Mara-Cartan identity, but then you want your derivative of this trivector object to involve some additional algebraic structures, and just by adding an index to what you had before, the idea is that the derivative of the trivector gives you some structure constant here, F tilde ABCD, with 3 antisymmetric indices upstairs. So this is not a set of Lie algebra structure constants, but it's can be viewed as a structure constants for a bracket of 3 elements. So that would be what's known as a 3 algebra. And there's a technical construction. Here I'm focusing on the 4-dimensional case, just for simplicity. The details depend on dimension, unlike in the Poisson-Lee case, Poisson-Lee T-duality case. So there's a construction known as exceptional generalized geometry, which captures the backgrounds that appear in 11-dimensional supergravity with a metric G and a 3-form, which they call C. The representation theory related to the exceptional groups is a little bit more complicated. I don't really want to go into it. But the idea is that you can construct combinations of the metric and the 3-form that give you quantities which behave nicely under U-duality. And for these special Poisson-Lee U-duality backgrounds, they factorize in a similar way, where you have some factorization where all the information about this underlying Poisson-Lee group appears in some set of generalized field binds, which obey an algebra under some natural Lie derivative, generalized Lie derivative. And this algebra is then inherited from basically from these conditions on D of L and D of pi. And so this is mimicking the structure of generalized T-duality. You get some underlying algebra from this generalized parallelization, which is termed an exceptional Greenfield algebra. It's not necessarily a Lie algebra. It involves these structure constants F and this 3 algebra structure constants F tilde in a complicated way. So the generators here are, there's a Lie subalgebra generated by these TAs. The indices A, B, and these T tildes are antisymmetric. So in this is a 4D example. There are 4 TAs and there are 6 T tilde ABs antisymmetric. That's the right representation structure to get an antisymmetric representation of the correct U-duality group, which is SL5 in this case. So you can check closure conditions or the compatibility conditions. You get things like the analogy of the Jacobi identity for the 3 algebra structure constants. what you also want to do is you want a rule to specify when you have a subalgebra. And your previous dualities in the Poisson T-duality case were about taking two different subalgebras of this sort of structure and then reading off what the dual background should be, knowing what the structure constants look like in these different representations based on different subalgebras. And so you can play a similar game here. The main difference with respect to the T-duality case is that there's no obvious symmetry between these F structure constants and these F tilde structure constants. The previous generalized T-duality was swapping F and F tilde. Here you can't do that because, well, one is a Lie algebra structure constant and the other is not, and the dimensions just don't add up. So if you like, this structure is the generalization of the structures that existed before, but it's a little bit more rigid and it might not allow you to find exactly the same types of dualities as beforehand. But nonetheless, it's interesting to explore because it allows you to sort of focus on sort of the backgrounds in 11 dimensions or in M theory that would share certain properties with the solutions that appear in generalized T-duality. So, for example, one could look at, okay, what are the sort of solutions that appeared in generalized T-duality after doing non-abelian T-duality? These were characterized by having some trivial structure constants F, but they had non-trivial dual structure constants F tilde. And so if you focus on that case, you should get something similar. So these are solutions which are somehow linked to the presence of a underlying tree algebra symmetry. So we call these tree algebra geometries. An interesting example is to directly generalize what you get from the non-abelian T-dual of S3 or SE2. So that would just be the case where you have this F tilde ABCD is just the four-dimensional alternating symbol. And you can solve the conditions for the Poisson-Lie group by taking this trivector object to be epsilon ABCD times some new set of four-dimensional coordinates XD. And that gives something which feels like a generalization of non-abelian T-duality to M theory. But okay, you have to actually construct explicit examples of backgrounds of this type. And then you actually have to ask, are they actually generalized dual in the sense I described before to something? Otherwise, you're just describing isolated solutions with some nice algebraic story, but there's no duality. So the way to do this is to exploit the full algebra that you get out of this construction. This turns out to be a Lie algebra known as CSO 401, or more familiarly as ISO 4, which is to say the Euclidean version of the Poincare group. So it's four-dimensional Euclidean rotations and translations. And okay, so the first thing you can check in this algebra within this Poisson-Lie duality proposal, is there another description of the same algebra which has the same structure and which has another dual subalgebra meeting certain conditions that allow you to immediately apply a recipe for duality based again on having a Poisson-Lie group with a different group and a different trivector. And that turned out not to be possible. Unlike in the Poisson-Lie T-duality case, that there just were no other examples after classifying all possible subalgebras, and none of them fit into the framework in the same way. That's kind of connected to the point I made at the start about this not exactly being a generalization of non-abelian T-duality itself. It tells you have to go slightly outside the framework. You have to relax some of the conditions about identifying the dual subalgebra. Alternatively, you can just use the fact that there's this direct link between this big exceptional twinfold algebra and the algebra that will appear in the low-dimensional theory that I will truncate to. So this generalized geometric formulation guarantees that you get a nice consistent truncation, and in this case it'll be to ISO 4 gauge supergravity in 7 dimensions. So this is what we're able to use to build new solutions. So we've identified on the right-hand side, we identified a particular prescription for building an 11-dimensional background that uses this trivector, which involves some pre-algebra structure constant. And this thing feels like it should be the right-hand side of a duality, like a non-abelian U-duality. And we know that this can be, backgrounds of this form can be reduced to a low-dimensional gauge supergravity with a particular gauging. And it's already known how to do these consistent truncations from a different starting point, completely different background, which is to take 10-dimensional 2A supergravity on a tree sphere with flux. So there's some horribly complicated ansatz in the literature that takes a 10D theory here with a particular form, 10D solution with a particular tree sphere factor, truncates it to a solution of a 7-dimensional theory. And then our investigations of generalized U-duality give us an alternative truncation from a different background in 11 dimensions to the same point. And so by my weak idea of generalized U-duality, I can relate solutions of this 10D theory on S3 to new solutions of 11D supergravity on this new geometry that is somehow specified by this underlying tree algebra structure and some underlying notion of a Poisson Lie group with a trivector. So this means we get something actually useful. We can get a way to generate new supergravity solutions and then explore their properties. So an example which we looked at is on the left-hand side to start off with this string and near horizon 5-brane solution. So this involves some 10D metric like this. There's a 3 form of this form, the important point being that there's some flux of the 3 form on the sphere that's needed for this ansatz to work. And we can do this truncation and uplift procedure using tools from generalized geometry to get a new 11D solution, which I write in all its glory here. So the parts highlighted in blue, if you like, these are the bits that directly resemble the non-abelian T-dual solution of S3. So you have this sort of 1 plus xx factor in the metric, and this 1 over, in this case, some function plus x squared. And then here in the brackets, we have some components of the 11-dimensional 3 form instead of the 10-dimensional 2 form. So you have, again, the same structure where you have basically hereCijk is epsilon tensor times x. In the non-abelian T-dual case, you had the 2 form B was epsilon ijk times x in 3 dimensions. This is a 4-dimensional generalization. And then there's a lot of extra conformal factors and things which are kind of required by the condition that this be an 11-dimensional solution. So, okay, it's a proof of concept. This is a brand new solution of supergravity. So what can we say about it? And it comes from a brane intersection, which is kind of nice. So one important comment is that, first of all, it's a local solution. We don't know anything about the range of those x's. We can find a global prescription to complete it by looking in the ADS limit, which corresponds to r squared f1 is 1. So there's a limit in which the solution takes some conformal factor times ADS3 times T4 times a radial coordinate, which you introduce times some sort of warp sphere factor. This, as I advertised at the start, this is actually can be fitted into a class of M-theory ADS3 solutions obtained previously. So these ADS3 solutions have a similar form. They're specified by a coordinate var rho, and these functions that appear are linear functions of rho, but actually they are required only to be piecewise linear. And then this rho takes values in some interval, and at different points inside the interval, the slope of these functions can change. And this is known to have some holographic dual, it's just some quiver field theory. And if you know about the holographic duals to non-abelian T-dual solutions, this is very similar and in some senses directly inspired by those constructions. And interestingly, our solution can be fitted into, let's say, the first subinterval of these general class of solutions with some particular coordinate redefinition and choice of these functions. And this is sort of exactly analogous to what happens to non-abelian T-dual solutions. And if these solutions have not already been found, having been inspired by non-abelian T-duality, this non-abelian U-duality elaboration could have instigated the same work. So it has very similar features to what you get from non-abelian T-duality, and so you can play the same games. So that's nice, and it kind of shows there's some common structure between these 10D solutions with linear bivector in non-abelian T-duality and these new 11D solutions with a linear trivector. They somehow both allow for ADS solutions with these sort of similar stories for the holographic duals. But we have a little bit more than the ADS limit. So we have this full solution, which came from let's say, we're not in the near horizon limit of the original fundamental string part of the solution. And I make this claim that the full solution can be viewed as a deformation of the ADS limit, and the deformation parameter, I say, is a 6 vector, which I will explain in a moment. So I've written up the solution in spherical coordinates. To guide the eye, I introduce a deformation parameter lambda by rescaling some of the coordinates, but it's more of an on-off parameter. I can always remove it by rescaling if it's non-zero. But it kind of shows that this thing looks a bit like a deformation or a U-duality transformation of something else. So lambda equals 0 is ADS, is the ADS limit I talked about before. You'll notice I've written the 3 form and its dual 6 form. There's a reason for that. So what one finds, what one can show, is that lambda not equals 0 is a U-duality transformation, if you like, E6 valued U-duality transformations. That means U-duality acting in 6 directions of the lambda equals 0 solution. What's weird is that this U-duality transformation acts on the T and Z coordinates, which are isometries, and it acts on the new 4-dimensional coordinates, which are not isometries. So it's quite a non-standard deformation by a U-duality parameter. There's a story then about what do E6 U-duality transformations look like, and some U-duality transformations look like shifts of the actual physical 3 form or its dual 6 form, but then non-geometric U-dualities have a geometric interpretation as 3 vectors or 6 vectors, and this particular U-duality that shows up here is a 6-vector deformation of the lambda equals 0 vector. So this is an unusual feature. It's quite an involved transformation. The last thing I'll say is that this happens really because it's a feature of the original solution. So it's some property which is inherited by the new 11D solution, but it's inherited in a way that brings in these non-isometric directions that make up the new 4D part of the geometry. So what is interesting is that in the original fundamental string NS5 grain solution, there's a similar story where the ADS limits can be viewed as, you can view the full solution as being a TST or O22 bivector transformation acting on the ADS limit, which is a sort of an honest T-duality, and at least in the sense that it's along abelian directions. What's interesting about this deformation is that it's been identified as being dual to a single trace version of the TT bar deformation of the dual C of T2. So then this much more complicated looking 6-vector transformation may be doing something similar to the holographic duals of this 11-dimensional solution, but I don't really know much more. I don't really have anything more to say about that. I just comment about it because I think this is an interesting link to some deformations, and it's intriguing the way that it's mapped to the new solution. You can be a bit more general. You can show in my most recent paper, you can show that if I start off with some initial solution which has 2 commuting isometries, which you can do honest T-dualities, these get turned into these funny non-isometric U-dualities of the 11D solution. which for this particular case of TST transformations give you these 6-vector parameters, where the 6-vector somehow is involving both commuting killing vectors as well as directions which are not killing, but which are linked, very much linked to the Poisson-Lie symmetries underlying the construction. So I come to my conclusions just in time. I think that generalized U-duality has some potential as a way to find interesting supergravity solutions. The inspiration comes from generalized T-duality, thinking about how it uplifts to M theory. And it certainly gives you a supergravity solution generating mechanism. Whether duality is too strong a word for it is maybe a different discussion, but I think it's interesting to try to explore this beyond beyond individual examples. If you go to higher dimensions, higher rank U-duality groups, you have more n-vector parameters. You have things like the 6 vectors. You can study similar ansatses in those cases. And briefly at the end, I mentioned that you saw in our solution these non-trivial deformations, which are U-dualities acting not just along isometry directions, but also along directions associated with these Poisson-Lie symmetry structures, where you don't have isometries, but you see instead these dual n-algebra structure constants appearing. So that's possibly some interesting direction to go, some new possible class of deformations with some nice algebraic interpretation. So thank you for listening. I hope this was technically audible, and then hopefully I'll see you next time.
Yes, Chris, thank you very much for the nice talk. So are there any questions from the people here in the audience? Yes. I'm sorry.
Okay. Is it possible to take some non-relativistic limit of U-duality? Could you?
As in a U-duality of a non-relativistic background?
Yeah, I mean, I know there is T-duality in non-relativistic sense, so I mean.
Yeah. Yes, you can do that. So in fact, it's convenient to use again exceptional geometry sort of techniques there. Yeah, you can describe some sort of membrane. So in the T-duality case, you have these stringy Newton-Cartan limits, which give non-relativistic backgrounds adapted to strings, and there are membrane and other brane versions of those, and you can dualize those, and some of the dualities will take you back to a relativistic theory, and others won't. I do have expressions of this form in some of my papers unrelated to this talk, actually.
Okay, thank you so much.
Okay, any further questions? I don't see any, so then let's, oh, you?
Hi, Chris, this is Sibylla speaking. Hey.
Hi.
Just not really a question, I think more just to clarify. So did I understand correctly that for this Poisson-Lie U-duality to work, you had to, so if you go to, can you go back to the exceptional Dreamfield algebra? So this first commutation relation on the T with a lower index, you had to generalize that to, well, so that you have not a subalgebra anymore, so you have an extra term there?
Yeah, basically a flux.
And the U-duality transformation, how is it acting at the level of this exceptional Dreamfield algebra then? So I cannot see it anymore as a swapping of subalgebras.
Yeah, no, it's a swapping of a subset of generators, but not between a subalgebra and a subalgebra. There would still be an action of SL5 transformation on the the generators that would take you to the new set that you want to identify as your physical 4, but then they just wouldn't be a subalgebra.
So
But
it's
I
like
think I do know what the transformation is.
So it's like scrambling the T with one index with the T with 2 indices, or
Yeah, it's probably you need to do some additional decomposition, and then you take some of the you take a few of the T's, take 3 of the T tildes and 1 of the T, and say they're my new isotropic subset. Yeah, so you need to choose an isotropic set of generators with respect to a certain notion of isotropic. You can realize that by a transformation, and you can do that for many cases. Just what you want to get at the end is you want to get something you can go back and write down the generalized frame for. And if you have a subalgebra, this construction, you immediately know what the generalized frame is. But then if it's something where it's not a subalgebra, you have some additional term on the right hand side, you need to modify it.
Okay.
And we didn't need to. So there are generalized frames for this CSO gauging that we could have used, but there was also this older style presentation of the consistent truncation that we used. But in principle, I mean, you could also do this generalization in the context of Poisson T duality, that you could allow to choose an isotropic set of generators that's not a subalgebra. And then you just need to work a little bit harder to know what to write down to construct the background.
Okay, thank you.
More questions? Okay, when there are no questions, then let's thank again Chris.
Okay, thank you.